In this video, we will solve logarithmic equations. A logarithmic equation is just what you probably guess, an equation that contains a variable with a logarithmic expression. And there are two types we're going to explore. The first is those that contain logarithms on each side of an equation, and the second are those that contain a combination of log expressions and constants. So the first type, we will use the one-to-one property of logarithmic functions, which states that the log to the base b of m equals log to the base b of n, then m has to equal n by the one-to-one property of log functions, right? The log of one expression equals the log of the other expression means that those arguments had to be the same. And so we will use this to solve equations such that if we have logs on each side, we'll just set the arguments equal to figure out the variable. The key thing that you have to remember, though, is that there are values that are restricted from logarithms, right? The argument of a log must be positive. So we have to exclude any solution that makes the argument of the log either 0 or negative. So in this example, we have the equation natural log of the quantity 3 plus 5x equals the natural log of x plus 15. So we have this equation where the natural logs are equal, so therefore the input of those logs have to be equal. That is, 3 plus 5x must equal x plus 15. And then we can solve this by subtracting x from each side and subtracting 3 to get 4x equals 12. And dividing by 4, we get x is equal to 3. Now we need to check, does this value 3 make either of the arguments 0 or negative? And if we replace x with 3, we get 3 plus 15, which is fine, or 3 plus 18, which is okay. So our solution set consists of the value 3. Example 4b is log of x plus 3 plus log of x minus 2 equals log 14. So this equation involves logs only, but we don't have a log of something equals log of something. So we're going to need to use the properties of logarithms to combine the log expressions on the left. And remember that when we have a sum of logs, that is equivalent to the log of a product, right? The product rule states that the log to the base b of the quantity xy is equal to the log to the base b of x plus the log to the base b of y. So therefore, we can rewrite the left-hand side as log of the product x plus 3 times x minus 2, and that's equal to the log of 14. Now we've written this equation as log of one argument equals log of another argument. Therefore, the two arguments must be equal. So we can state that x plus 3 times x minus 2 is equal to 14. Now we have a quadratic equation. When we multiply this out, we'll need to set it to 0 and solve. So we get x squared minus 2x plus 3x minus 6 equals 14. Combining like terms gives us x squared plus x, and then we have to subtract 14 from each side. So we get x squared plus x minus 20 is equal to 0. So we can solve this by factoring. We think about the factors of 20 whose difference is 1. That would be 5 and 4. We need different signs on the 5 and 4 with a plus sign on the larger factor. So x plus 5 times x minus 4 equals 0. Now we can set these equations or factors equal to 0 to get x plus 5 equals 0, or x minus 4 equals 0. Therefore, x is equal to negative 5, or x is equal to 4. Now before we can write our solution set, we need to examine whether or not these values make the arguments 0 or negative. If we replace x with a negative 5, notice that negative 5 plus 3 is a negative 2, so that makes that log expression undefined, so I need to exclude this extraneous solution. If I substitute 4 for x, 4 plus 3 is fine, 4 minus 2 is fine, so 4 is our solution. And then part C is log of x plus 4 minus log 3 equals log of x minus 2. So here again we have only logs in our equation, but we have a difference of 2 logs on the left. So recall the quotient property that states if I have the log of a quotient x over y, this is the same thing as the log of x minus the log of y. So I'm going to rewrite the left side by combining these 2 logs to the log of the quotient x plus 4 divided by 3. And that's equal to the log of x minus 2. Now we have 2 logarithmic expressions equal. By the one-to-one property of logs, their arguments must be equal. So we said x plus 4 divided by 3 equal to x minus 2. To solve this equation, we need to multiply each side by 3, and that will give us x plus 4 equals 3x minus 6. So we can subtract x from each side and add 6. So we get 10 is equal to 2x, and divide by 2 gives us x is equal to 5. Now again, I have to check, is a log defined for 5? And 5 plus 4 is 9, 5 minus 2 is 3, so that is correct. Now, type 2 logarithmic equations are those that involve both logarithmic expressions and constants. So our goal in this type of equation is to get the log isolated to one side equal to a number, and then we're going to rewrite that logarithmic equation into an exponential equation, right? So remember that our base b to y is equal to x is equivalent to y equals log to the base b of x. Again, the steps outlined are collect all log terms to one side, constants to the other. Then we will apply the log properties to condense the sum or difference of logs to one term. And then we'll convert that logarithmic equation to its equivalent exponential form, solve the equation, and then discard any of our extraneous solutions, which are values that make the log expression negative or 0. So in example 5, I have log to the base 4 of x plus 5 equals 3. So here my log expression is isolated. I want to convert this to its exponential form, which means that 4 to the third is equal to x plus 5. Well, 4 cubed is 64 equals x plus 5. So I can subtract 5 to get 59 is equal to x. And the 59 does not make my argument 0 or negative, so the solution set consists of 59. Hopefully you're seeing the connection, right? To solve the log equations here, I'm having to convert to the exponential form. To solve the exponential equations, I had to apply logs, right? Inverse operations. B is 5 times the natural log of x equals 20. So I need to isolate this natural log by dividing each side by 5. And so I get natural log of x is equal to 4. And now I need to convert this to its equivalent exponential form. I need to recall that my base of natural log is really understood to be e. So I'm saying e to the 4 is equal to x. And that is my precise solution. If you wanted to use your calculator to figure out what e to the 4 is, you could actually do that. But I'm just going to leave it in this form, e to the 4. Part C is log to the base 2 of x minus 1 equals 3 minus log base 2 of x plus 1. So notice that I have logs and a constant term. So to solve this equation, I need to collect my logs to one side. So I'm going to add the log base 2 of x plus 1 to each side. So this gives me log 2 of x minus 1 plus log base 2 of x plus 1 is equal to 3. Now I need to combine the two logs, recalling that the sum of two logs is a log of a product. So this is rewritten as log base 2 of the product x minus 1 times x plus 1 is equal to 3. And now I need to convert this to its equivalent exponential form. 2 to the 3 is equal to this argument. So 2 cubed is equal to x minus 1 times x plus 1. Simplifying, I get 8 equals x squared minus 1, right? Those are conjugates, so when I multiply, I get the difference of squares. I can add 1 to get 9 equals x squared and apply the square root property, which says x is plus or minus the square root of 9, which is 3. So I have to check between negative 3 and 3, or either one of those extraneous. If I replace x with a negative 3 minus 1 is a negative 4, which makes that log expression undefined. So I have to exclude the negative 3. If I replace x with 3 minus 1 is fine, 3 plus 1 is fine in the other log, so my solution set is just simply 3. And then part D is log base 2 of x plus 2 minus log base 2 of x minus 5 equals 3. So here again I have logs and constants. My logs are already on one side of the equation, but I need to combine them to get a log of a single expression. A difference of two logs is a log of a quotient. So this is equivalent to the log base 2 of x plus 2 divided by x minus 5 is equal to 3. Now converting to the exponential form, this means 2 to the 3 is equal to this argument. So 2 cubed is equal to x plus 2 divided by x minus 5. So that's 8 equals x plus 2 divided by x minus 5. Multiplying each side by x minus 5, I get 8x minus 40 equals x plus 2. So I can subtract the x to get 7x, add the 40 to get 42, and then divide by 7 to get 6. And notice that the 6 does not make either one of my arguments 0 or negative, so my solution set consists of 6.